we are going to discuss about the filling of electrons in an atom. The first thing is that the number of electrons, how many electrons we have, that determines the number of orbits. Depending upon the number of electrons, the number of orbit will be determined. And the number of protons, depending upon the number of protons, the electrostatic interaction between the nucleus and the electrons will differ. So if you have more number of protons, the electrostatic interaction will increase, and when you have lesser number of protons, the electrostatic interaction will decrease. For example, you can see here in case of hydrogen, we have one proton and one electron here in first orbit. In case of helium, we have two protons and two neutrons in the nucleus, and we have two electrons in the first orbit. In case of lithium, we have three protons and four neutrons. You see, these red ones are the protons and these blue balls are the neutrons. So we have three protons and four neutrons, and we have two electrons in the first orbit, this one and this one, and another one electron in the second orbit, this one. Now in case of beryllium also, the next electron also comes in the second orbit. So now we are going to learn how these electrons will come and how many electrons we can fill in orbitals. So those things we are going to learn. So if you see this diagram, so first we have hydrogen. In case of hydrogen, we have only one electron. That one electron will come and fill in this first orbit. I'll make a cross sign to denote the electrons. In case of helium, we have two electrons, and both the electrons will be filled in the first orbit. One electron here, another electron here. Now in case of lithium, when we add another electron, so first two electrons will go in the orbit number 1. You can see here, first two electrons will be filled in the first orbit. Now the next electron, the third electron, will be filled in the second orbit. Now one by one we will put electrons in the second orbit, and you can see after that lithium we will get beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And let's see in the case of neon. So in the case of neon, we have two electrons here, 1, 2, and we will have 8 electrons. One by one we have put 8 electrons in the second orbit. 3, 4, 5, 6, 7, and 8. So in case of neon, first two electrons are in first orbit, and next 8 electrons are there in the second orbit. Now when we have another electron coming, in case of sodium, so that one electron will actually occupy the third orbit, and then we will put one by one electrons in the third orbit. So as you go along this period, you put one by one electrons in the same orbit, and after this inert gas, when you put one more electron, that electron goes in the next orbit. So here you can see the putting of electrons here. For example, here in the hydrogen there is one electron. In helium we have put two electrons. Now when we add another electron in case of lithium, that goes and takes the second orbit. Now we put electrons one by one in the second orbit. 5 electrons in case of nitrogen, 6 electrons in case of oxygen, 7 electrons in case of fluorine, and 8 electrons in the second orbit in case of neon. And then when we want to put one more electron, that will go and take house in the other orbit, third orbit. And again we will feel electrons here, and in case of argon we will have 2 electrons in the first orbit, 8 electrons in the second orbit, third again 8 electrons in the third orbit, and again when we put one more electron in case of potassium, that will go and fill the fourth orbit. So likewise we feel electrons one by one in one atom. This is just for conceptualization. Now we will go into more details. Before that, if you see the periodic table of elements, atomic radius, so this periodic table gives you the size of the elements. If you see these left ones, they are in bigger size, or these spheres are bigger in size. That means their atomic radius is bigger. And as you go along a period, here from left to right, the size decreases. Now, why it happens? So from left to right, when we are going, now we are putting more and more electrons as well as protons. From left to right, the number of proton is also increasing. So when we increase the proton number, so that time the electrostatic attraction between the nucleus and the electrons increases. So as the attracting power increases, so it's like a, see, we have proton here, and then surrounding it we have electrons, right? Just sorry, I'll erase it. Just a second. So we have nucleus, and then surrounding that we have electrons and different shells of electrons. Now assume this nucleus is a girl, and these electrons, those are actually boys. Now when we put more and more protons, so the girl is more and more attractive. So that time this nucleus, sorry, these electrons, means the boys, they try to come close. So these shells will come close. These orbits will try to come close because the girl is very attractive. The more number of protons are there, so as the girl is more attractive, the electrons, the boys, they will try to come close to that girl. So the orbit will shrink because the electrostatic attraction is more. The electrons will try to come close to the nucleus, or the positively charged nucleus, or positively charged protons. So as the girl is more and more attractive, as the number of proton is more, the electrons or the boys will try to come more and more close. So that's why the size actually shrinks from left to right in a period. These things I will discuss in detail in the next lecture, lecture 6. Do not miss that. That is a very important lecture, and I will discuss each and every periodic trend and their why is it happening, and the detail I will discuss in the next lecture. This is just to give you a preliminary idea that how, if you increase the number of protons and electrons, so how the size will shrink, and if you increase more and more electrons, how it will be filled in the orbitals or orbits. So next we will come to the discussion of orbits and orbitals. So for this, let's think this is your home. Just let me draw a home for you. Just think this is your home, and this one over here is your school. School generally has a bigger gate, right? And all the classrooms, they have small windows. Oh, sorry, my drawing is pretty bad. So this is your home and this is your school. Now from home to school, you can go either by walk, or you can take a cycle and roam here and there, here and there, here and there, and then you can go to the school. Or when your father is free, he can tell you that come son, we will go by our car today. So you can take a car and you can take a main road and you can go like this, right? So there are different possibilities. From home to the school, the distance is same, but still there are different possibilities, right? You can go simply by walk, or you can go by cycle, or you can go with your father with a car. So different possibilities are there. So similarly, for the electrons also, they have different possibilities or probabilities. So they can occupy different paths or different portions of a orbit. Now let's try to understand the definition of orbit and orbitals. So an orbit is designated as the path for electrons to revolve around the nucleus. So this is actually a two-dimensional conception, that the electron is rotating around the nucleus. So here this yellow one is the nucleus and the electrons are rotating around it. So if I draw like this is the protons or the nucleus, sorry, and in this path the electrons are circulating. My drawing is pretty bad in this one. Actually, I'm using a very bad setup. Yeah, so this one is your proton and your electron is revolving around it. So this is a two-dimensional picture, and this one here is called orbit because this is a two-dimensional thing. And I have just given or designated the path in which the electron is revolving around the nucleus. Whereas an orbital is the 3D space around the nucleus where the probability of finding an electron is maximum. So inside this same path, we have different three-dimensional space. For example, in your case, you can take different travel mode to reach to the school. Similarly, electron can take different 3D space to orbit that nucleus. So an orbital is the 3D space around the nucleus where the probability of finding an electron is maximum. So as we discussed that orbitals are the 3D space occupied by electrons where the electron density is maximum. So inside one orbit there can be different orbitals. For example, when we have orbit number 1, 2 and 3, which are also known as K, L and M. So in that case, in orbit 1 we have only one s. So that is only one orbital, 1s. In case of second orbit, we have 2s and 2p. In case of third orbit, we have three different orbitals, that is 3s, 3p, and 3d. Similarly, in the fourth orbit, we have 4s, 4p, 4d, and 4f. Now, let's see the shape of s orbital. So, s orbital is actually spherical in nature. So, this one you can see spherical shape. This is the shape of s orbital. So, electron density is almost same in the all directions, and it takes a shape of a sphere. Now, this is for 1s. So, if you go to the 2s, that will be a bigger sphere. Compared to 1s, the 2s will be a bigger sphere. Similarly, the 3s will be much bigger sphere. Now let's see the p orbitals. P orbitals are having three different compartments. So these are called px, this one is px, this one is py, sorry, this one is pz, and this one is py. Oh, sorry. So p orbital has px, py, and pz. These three different compartments. Now these p orbitals, they look like a dumbbell. You can see in center the electron density is 0, and as you go further from the nucleus, the electron density increases. So it actually looks like a dumbbell. So in the center the electron density is 0, and as you increase the r, go along as you go away from the nucleus, the electron density increases. So these are kind of like this, dumbbell shaped. So if there is only one dumbbell, that is p orbital, and in case of d orbital there are actually two dumbbells. So as I have drawn this shape, this looks like the d orbital. Now in case of d orbital, so we have five different orbitals. So these are named as dxy, dyz, dzx, dx square minus y square, and dz square. Similarly, f orbital, it has seven different compartments. So these things I will discuss in some later videos. I will make dedicated videos to discuss these things. But for the time being, we will see this video which I have taken from this channel scienceviz.com. I will put this link in the comment or description. If you want, you can go and check this video. It's a very nice video. From this, you can conceptualize how these electrons are revolving. Now, I'll show it. So first we have this electron. Here, this one is the nucleus, or just write P, or proton, positively charged nucleus, and this electron is revolving around it. Now in the 2D space, we can see that electron is circularly moving, but actually in the 3D space, it will be uh, it will create a sphere. So the electron density will be like a sphere. Let's see. In case of 1H, we have one proton and one electron. So the electron is circulating that proton. So in the 2D direction, we can see only like a circle. But when we see the 3D space, it is actually a sphere. And the electron density is equivalent in the entire sphere. So this is in case of proton. In case of 1H, hydrogen. Only one electron. Now if we add another electron, so that means we have two protons and two electrons. We are adding another electron. In case of helium, both the electrons will occupy 1s. That's why we write 1s2 in case of helium. Now when we add another electron, that will come, and that cannot take 1s because 1s is already filled, so that will take 2s, and that we get lithium, 3 protons and 3 electrons. Now we add another electron, that will also go and take 2s, so we get beryllium, 2 protons and 2 electrons. Now when we add another electron, that goes in the p to p. In case of boron, that takes p, or it can be sp2 hybridized. This is how it will look in the sp2 hybridization. Now when we add another electron, in case of carbon, it can either take sp2 and 2p. This is the 2p and sp2, or it can become sp3 hybridization. This is how it looks when carbon is sp3 hybridized. Or it can be sp2 hybridized and one electron can be in the 2p. This is how it will look. or it can be sp hybridized and 2 electrons can remain in the 2p. So this is how it will look. So there are different hybridizations. Based upon that, the electrons can occupy different 3D spaced or different orbitals. So these things, just take a note. These things we will discuss in detail for some other videos in other chapter. So that time I will discuss in details about these things. Now let's see the electronic configuration. So in case of hydrogen, we have seen that the hydrogen, the electron will go in the 1s orbital. So that we write like this. So this box means one orbital and this one is 1s orbital. So in case of hydrogen, the first electron goes in 1s. Then in case of helium, we have two electrons. So both the electrons goes in the 1s orbital. And each and every orbital can take only two electrons or up to two electrons. When we have another electron, that will go in the 2s. Now when we add another electron, that goes also in the 2s, and these arrows actually denote spin. So for electrons you have to write like this. This is called up spin and this is called down spin. When we have only one electron, we write it as up spin, and when the second electrons come, we add the down spin. In the same orbital, both electrons cannot have same spin. Okay, just try to remember this, that if there are two electrons, both electrons cannot have same direction. One will be up, one will be down. So in this case, this is up spin, and when we add another electron, that electron becomes down spin. In case of boron, we add another electron in the 2p, and this one is the 2p, which has three orbitals, 2px, 2py, 2pz, and in total it can accommodate 6 electrons. So let's see, in case of proton, the electronic configuration is 1s1. I'm saying proton, this is actually in case of hydrogen. In case of hydrogen, the electronic configuration is 1s1. In case of helium, the electronic configuration is 1s2. In case of lithium, another one electron comes and that occupies 2s. So the electronic configuration becomes 1s2 and 2s1. In case of beryllium, the next electron also takes 2s. So 1s2, 2s2. In case of boron, the next electron takes 2p. So the electronic configuration becomes 1s2, 2s2 and 2p1. In case of carbon, we have 1s2, 2s2, 2p2. In case of nitrogen, it will simply become 2p3. In case of oxygen, it will become 2p4. In case of fluorine, it will become 2p5. And in case of neon, it will become 2p6. Now, in this case, 1s2, 2s2, 2p6, total electrons are 10, and it is inert gas element. After that, whenever we add another electron, that will go in the 3s. So in case of sodium, we get 1s2, 2s2, 2p6, 3s1. Then in case of magnesium, it will become 3s2. In case of aluminium, when we increase another electron, that time it goes in the 3p, and we get 1s2, 2s2, 2p6, 3s2, 3p1. Then in case of silicon, we add another electron in the 3p, and we add another electron in phosphorus, sulfur, chlorine, and argon. So again, in case of argon, the last electron is going in 3p, and we get the electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6. Now as the 3p6 happens, so the orbital is closed. Now if we add another electron, that will go in the next orbital, that is 4s1. So in case of potassium, we get 4s1. In case of calcium, we get 4s2. So this is called the filling of electrons, how electrons are getting filled one by one, in which orbital, and which orbital will come first, which orbital will come next, that we are going to learn later in this video. So the thing you have to remember is that how these electrons are getting filled, and it cannot accommodate more than 2 electrons. The orbitals cannot accommodate more than 2 electrons. So to understand this filling of electrons, we will learn Aufbau principle. Now we have seen that in the first period we have 1s, in the second period we have 2s and 2p or second orbit. In the third orbit we have 3s, 3p, 3d. In the fourth orbit we have 4s, 4p, 4d and 4f. Similarly in the fifth orbit we have 5s, 5p, 5d, 5f and 5g. Now when we are filling electrons, first we fill 1s, next we fill 2s, next we fill 2p and then 3s. So we are coming actually from this end. First we fill this and then we fill this. Then we fill 3p. And after filling 3p, so you cannot simply fill 3d. You have to go to 4s. And now after filling 4s, you cannot simply fill 4p. You have to actually fill 3d first, then 4p and then 5s. So that is why this arrow. So this arrow means first we are filling 1s, then we are filling 2s, then we are filling 2p, then 3s, then 3p, then 4s, and then 3d, then 4p, 5s. This seems very hard to remember, right? So that's why you can remember this alternative path. This is how I remember this electron filling orbitals. So I remember like this s. So this is a lonely s, just one s. Now here s has p, so s is not single anymore. When it has a partner, I write square because it is not single anymore. So first it is s, then sp square, sdp square, sfdp square. Then what? Now what does it mean? So first when the electron will come, that will fill s, and again it will be sp square, means next line it will be s and p, and again there will be another sp because it was sp square, right? So s, then sp square, now sdp square. So next line there will be s d p and again another sdp because it was square. Next it will be sfdp square. So again next I have to write s, then f, then d and p. Similarly I have to write another sfdp which I am not writing. Now what I will do, so this is kind of pyramid like order, right? First we have s on top, then sp, again sp, then sdp, again sdp. Now you have to remember, so these s and p are actually ns np, means this one is the first row, right? So this one will be 1s. Now this s and p, these are in the second row, so it will be 2s, 2p. This one in the third row, 3s, 3p. And next this one is the fourth row. According to which pyramid I am writing, this one comes in the fourth row, so this one will be 4s. Now in case of d, you have to write n minus 1. In case of s and p, it will be nsnp. In case of d, it will be n minus 1d, and in case of f, it will be n minus 2f. So this one is the fourth row, so I will write 4s, and n minus 1 means 4 minus 1, so 3d, and then 4p. Now again this one is the fifth row according to my pyramid, so I will write 5s. This one will be n minus 1, so 5 minus 1 means 4d, and again this one is the np, means 5p. And in case of this one is actually 6s, and in case of f we have to write n minus 2. So in the sixth row it will be 6 minus 2 means 4f, and d will be n minus 1, so 6 minus 1 it will be 5d, and again np, so 6p. So I remember this pyramid, and whenever I am doing any electronic configuration, I will quickly draw this S, SP, SP, SDP, SDP, and SFDP. So first, electron will be filled in 1s, then 2s, then 2p, then 3s, 3p, then 4s, 3d, 4p. After that 5s, 4d, 5p, then 6s, 4f, 5d, and 6p.
Hey genius, I hope you liked the video and the concepts are clear. So if you want to know more and if you want to learn more, you can go and check the periodic table and periodic trends folder. I have already uploaded 7 lectures on this topic. Please go and watch all those 7 lectures. I hope it will be very useful for you. And if you think these videos are knowledgeable, please share it with your friends and don't forget to subscribe. Okay? Thank you. Bye bye.